Hey scholars, it's good to be back with you. Today I'd like to talk to you about polynomials and nonlinear equations. Now these are things you've probably seen before in maybe an algebra class, maybe a long time ago. They're really important, so important that they're worth a class, and also there are specific solutions for some of these that you've been taught but maybe need a reminder of. So let's start by talking about polynomials. Well, what's a polynomial? Polynomials are equations of a very specific form. This is the form. All right? So the C's, C1, C2, C3, all that, those are just numbers. Those are scalars. They can be real numbers, they can be imaginary numbers, they can be fractions, whatever, but they are numbers. X is raised to an integer power. It looks like there's one missing there, doesn't it? Well, not really. I gave myself a little space to write this. That's actually x to the 0. Well, x to anything to the 0 power is 1. So we typically omit that. There really, technically, is a 1 there, too. Mathematicians like to write things as compactly as they can, which makes sense. If they didn't, it would get cumbersome pretty quickly. So that's usually omitted, and that 1 is usually omitted. Now, how far can this go? I don't know, as far as you want. You can go to the largest power that makes sense for you or is required in your calculations. When we talk about orders of a polynomial, what the heck's an order? Well, the order is just the biggest exponent. So if I were to stop right there, that would be a third order polynomial. One that you'll see a lot, we study a lot, is a second order polynomial, which also gets called a parabola or a quadratic function. Different names for the same thing. Last thing you need to know about polynomials is that they have a very specific property in their solutions. Well, wait a minute, what's a solution? Let's try this. If I wrote out, I'm going to look at my screen here to make sure I get this right. Okay, minus x squared. Okay, that's a second order polynomial. That'd be a parabola. Parabola is the shape you get when you plot that. Right? When I say it has a solution, what I really mean is what are its roots? When it's looking for roots, what you're trying to do, in fact, I'm going to get this out of the way here, is you're trying to find an x that makes everything on the left side of the equation, makes the whole polynomial equal 0. Well, why would you want to do that? Well, lots and lots of physical things that we care about can be described with one or sometimes a system of equations. And you can always do a little bit of algebra, add an addition and subtraction to get it into the form where something on the left side of the equation equals 0. You can always get your equations to look like this. Now that you have, now you're doing the same operation on all your equations, and that's called a root or a 0. In MATLAB, it's called a 0 function. There's also a function called fsolve that does the same thing. So wherever you started, you can always turn it into that. And once you're turning it into that, those one or two functions in MATLAB will be useful no matter what's on the left-hand side. That's powerful. So this is a big deal to find roots or zeros. Now, parabolas, second-order polynomials, have an interesting property. That is that they have as many roots as there are, the number of roots equals the highest power. What they may have told you in I don't know, junior high algebra class probably, is that it crosses the x-axis as many times as the highest power of the exponent. Well, what that would mean is if you had a second order curve, it might look like that, and it has two roots. Because remember, this is y, okay? I can call it anything you want. I had called it p, but if you, for the purposes of plotting, if you want to call this y, you can. When y equals 0, find an x so that y equals 0. That's x, that's y. So when you're finding y equals 0, you're finding a root. This is the graphical equivalent of that. Alrighty? Now, say I've got a third order polynomial. Well, let's just take a different color here. Third order polynomial would cross that axis 3 times. Now, if you're getting a little ahead of me, you might say, well, sometimes there are polynomials that don't cross the axis. They don't cross the axis if you insist that x and y be real. Once you allow them to be complex, they cross the axis again. Now that's a couple lessons down. Well, I'll go over that in more detail. Okay, so how do you solve this? How do you find an x that makes that equal to 0? In fact, I'm going to get rid of this again. So how do I make sure that equals 0? Is there some kind of closed form expression? For second order polynomials, there is, and you probably, again, remember this from, I don't know, again, probably junior high school. Yeah, let's do this. Okay, there it is. To find the roots of this, you can use this. It's called the quadratic equation. Only what's a, b, and c? Now up here I wrote it C0, C1, C2, C3, and so on, because I'm never going to run out of c's. If I insist on it all having the same individual letters, there's only 26 letters. I don't need this anymore, so I'm going to get rid of that. So the way they normally write this in your algebra class is a polynomial that's second order. Whoops. Polynomial that's second order, we can put a 2 down there if you want, is ax squared plus bx plus c. All right, that's typical. You see this absolutely everywhere. So let's compare this equation. Well, let's see. A is, I'm going to write this up here maybe. A is minus 1, because remember there's a 1 implied there. That's actually minus 1 times x. B is 2, and C is 4, all right, for this equation right here. So let's just do what the equation says. Now that I know what that is, I'm going to get this out of the way because it's kind of not where I want it. So let's just do what this says. Now let's see. Minus 2 plus or minus okay, just do that. Now what is it? 1, 2. Why is there a 1, 2 there? Well, there's two roots. One of them corresponds to plus that square root, and the other one corresponds to minus that square root. Let's make sure we know that goes to there. Let's just do that. Minus 2, 4 plus 16. Well, dang, this is easy. All right, so that's, let's see, minus 2 plus or minus a square root. Let's see, 4 plus 16 looks like 20, so that's 4 times 5. Okay, can you see down here if I write? I have just enough room here. Equals minus 1 plus or minus square root of 5, I think. Is that right? I think that's right. So that's plus 1 plus or minus the square root of 5. All right, well, what is that? If we work that out, what do we get? I'm going to go back over here because I'm running out of space on my board. So just so we know what those numbers are, it works out to, I have on my screen over here, I'm kind of trying to make sure I get this right. Okay, x1 is minus 1.236. I'll get my head out of your way here in a second. Let me just write this down. Okay, those are your two roots. Now, if you're not a mathematician, if you're a physicist, engineer, something like that, the temptation is to say, what does this mean? What does it inherently mean physically? Well, maybe nothing. This is a mathematical relation that is true. To a mathematician, that's all it is. To somebody like me who's trained as an engineer, I care about this because it represents something in the physical world that I want to know about. Now, it may be something as abstract as when I go onto Excel and I hit the add trend line button for some data, that when I say polynomial order 2, that might be what I'm getting. So in the curve fit through all this data that might be measured, a curve fit tells me something about the real physical world I want to know about. But to a mathematician, this is just a relationship that is true, and that's the end of the story. And that's as it should be. It's up to us to decide, okay, now that the mathematicians have given us this tool, what can I do with it? Where's the utility? So the next thing we're interested in is what's a nonlinear function? What's a linear function? Well, they're just what they sound like. If I plot a function and I get a straight line, it's a linear function. That's true, but it's not complete. So let's flesh that out a little bit. If I were to just simply erase that and get bx plus c, and I'll get rid of that 2 here to make this a 1, that's a straight line. That's the same as y equals mx plus b that you might have learned in, again, probably junior high school. We're just using different variables to assign to the numbers. But it's the same thing mathematically. That's a straight line. Well, this is a straight line in 2 dimensions. If I make this plot on a piece of paper or a screen, well, that's a straight line. But what if I'm thinking in higher orders? What if I have 2 independent variables and 1 dependent variable, and I want to plot it in 3D? Is there such a thing as a linear function in 3D? You bet. Here's what it looks like. I'm going to get rid of that. I'm going to start over. Let's say z is my vertical axis, so that x and y are now my independent variables. Is that a straight line? Well, sort of. It's the equivalent of a straight line, but it's the generalization of a straight line in 3 dimensions, which is a plane. Probably the more correct way to say this is the curvature of this surface is 0 everywhere. It's flat everywhere. That's true in 2 dimensions. Well, 2 independent variables, 3 dimensions. Could it be true in 4, 5, 6, 7? Yes, of course it can. Right? One of the big ideas of mathematics that I hope you're picking up, but in case not, let's just touch on it here, is that mathematics is general. When you have a concept in mathematics, it tends to extend broadly. If you want an example, think of addition. That's about the simplest mathematical operation there is. The concept of addition exists independent of what entities you're trying to add. So can you add integers? Yes. Can you add fractions? Yes. Can you add decimal numbers? Yes. Can you add complex numbers? Yes. Can you add functions? Yes. Can you add vectors? Yes. Matrices? Yes. Although those two, there's some, you got to get the sizes right. There's some restrictions. But the idea of addition holds. So addition is addition. The mathematical entity to which you're applying addition is more of a specific case. So the idea of linearity is a general idea. You could apply it to a 2-dimensional space and get a straight line. You could apply it to a 3-dimensional space and get a plane. I don't know what it would be in 4 dimensions. I don't know about you. I live in 3 dimensions. I don't know how to live in 4 dimensions, so I don't know what that would look like. But the mathematics is very clear and very well understood. So if you can, when you generate a surface line, whatever, and the slope or the curvature is 0, that's a linear function. So let's go back to, in fact, let's go back to the simplest straight line in 2 dimensions, x and y. You learned this in, like I say, probably junior high school. That's a straight line. That's a linear function. I only have to do a little bit to make it nonlinear. I do anything that keeps this from being a straight line. Let's do that one again. Definitely not a straight line. Oh, not a straight line anymore. So anything I do to change that it's going to be nonlinear. Linear functions, for reasons we're going to find out a little later, are easy to solve. In fact, there's a field of mathematics called linear algebra that's very powerful. You'll certainly need it. When you go from systems of linear equations to systems of nonlinear equations, they get hard to solve. Sometimes they're really hard to solve. So we tend to approximate the physical models linearly if we can. So how do you solve a nonlinear equation? Well, it's tough. There are many equations for which there just isn't any closed form solution. In fact, I'd venture that most nonlinear equations don't have closed form solutions. How many nonlinear equations are there? Of course, there's an infinitude. I don't know how you break those into fractions or into proportions, but it's safe to say that if you're looking at a nonlinear equation, it's highly likely that there's no closed form solution to it. Let me give you a simple example. I use this one a lot. You may have seen it before. How about this? Okay, that's a nice jaunty little equation. It looks like it's only got 2 terms. How are you going to solve it? What does solving it mean? Well, you can write it this way. Find a value of x for which cosine x equals x. That's mathematically correct. You could write it as a root function, like I said before. There. You could do that too. They're mathematically equivalent. It doesn't matter which one you do. Well, this one's going to be tough. Let's start with the original. So, if you're going to solve this, you're going to need to get an expression where x is on one side of the equal sign and there's something else, a bunch of numbers that you can calculate on the other side. How are you going to do that? Well, how about inverse cosine? I'm going to put add the parentheses there just to keep it from getting, oops, that's not right anyway. Let's do it this way. Okay, I've taken the inverse cosine of both sides. Now, the equation is still an equation. If you do the same thing to both sides, I did the same thing to both sides. So this comes out to that. All right, well, true without being helpful. Where do I go next? Well, if cosine x equals x and inverse cosine equals x, I guess I could write this. Also true, but I'm not getting anywhere. I don't know of any way to get x equals something out of this. The best I can think of is if we approximate this with a polynomial, you might get somewhere. You'll get an approximate answer. Bottom line is there's no closed form solution to this. There's no quadratic equation or anything that's going to work on this. And this is generally true. When you see nonlinear equations, it's safe to assume there is no closed form solution. You have to do it numerically. All right? So with this in mind, let's go over to my computer and let's start seeing what MATLAB can do for us. Analytically, this is a complete dead end. MATLAB has absolutely no problem with this. This is a very, very simple problem for MATLAB. So let's do that.